Let me talk you through this load calculation exercise. This first one gives the phosphorus discharge limit for wastewater treatment plants, and it gives a flow range, and then for that flow range, what concentration you can put out. And I was curious what kind of mass that gives us. Now, for the first one and last one, it doesn't give us a number, but it does for those middle three. So I'll show you one calculation for those middle three. I did it on a spreadsheet, but I'll write out the calculation and you can do the other two. So the upper end of this range is 15 million gallons per day. And we have 1 milligram per liter. So how much mass does that give us? So I'll write here 15. I'll write like this: m gallons per day times 1 milligram per liter. And then I got to get the units to give me, am I asking for kilogram per day or kilogram per year? So you could go through the units on that. Here's a handy dandy one they use a lot in wastewater and a few other things. There's a unit conversion, 8.34 pounds per million gallon per milligram per liter. So milligrams per liter cancels out. Million gallons cancels out. And so we have pounds per day. So that's how they get pounds per day. And again, you can do other ways through the units. That's pounds per day, and I want kilograms, so it's pounds on top, so I want 1 kilogram is 2.2 pounds, and that will give me kilograms per day. And if I want years, I still have day there, I have 365 days per year. So it's 365 and a quarter, right? Leap year. So that gives me, for that one, it gives me about 125 pounds per day or 57 kilograms per day. So roughly 21,000, it's 20,000 something, 21,000 kilograms per day-ish. So to do that for the other two as well, again, mine looks a lot neater in a spreadsheet than it does here, but I'll move on to the next problem. 1,000-foot long stretch of stream bank eroding at 0.5 feet per year. And this is like an actual calculation. Did talk with, I'll name Matt Van Epps of Arkansas, and I've seen him present his stuff a few times, but this is kind of one they actually do. So I have 1,000 feet long bank, and I'm going to do a section that's 6 feet high. Obviously, you have a little more real life, a little more variation than geometry. And then it's eroding at, I'll see if I can do this here, 0.5 feet per year. So I want to know how much soil is in this box. I'll do, and then how much phosphorus is in there. So first of all, we have just the volume of it, or volume per year. We have 1,000 feet times 6 feet times 0.5 feet per year. So that's 3,000 cubic feet per year of soil that's going down the stream. So I want to know how much phosphorus is in there. 50 parts per million. I have volume of soil. Parts per million is 50 milligrams of phosphorus per kilogram of soil. So I need to get from this volume to a mass of soil, the kilograms of soil. So I take that times the bulk density. You've probably at this point done the groundwater unit already. So if you did it in order. So the bulk density, it's not given. A typical one, these are estimates, right? this very nature of this, I mean, if you get it within 100% of what actually happens, like half or double what actually happens, that's really good. But so I'm not going to worry about if this is 1.59 or 1.42 or something. So it's about 1.5 as a typical value, and that's could be grams per cubic centimeter or 1.5 multiply top and bottom by 1,000 be kilograms per liter. So I do unit conversion again. We get 3,000 cubic feet per year times 1.5 kilograms of soil per liter of soil. And then units happen. And I didn't spreadsheet. I don't have the units written down here. And then I have times soil, 50 milligrams of phosphorus per kilogram of soil equals, not as much as you might think, but I'll write again here. Units happen. So obviously I can convert units in there, but that's what that's asking for, is calculate that out and get a mass of actual phosphorus that's going downstream. By the way, on the units, remember, so if kilograms per liter, it's 1,000 liters per cubic meter. It's 1,000,000, 10 to the 6 milligrams per kilogram, 1,000 grams per kilogram, 1,000 milligrams per gram. I should probably have feet cubed to meter cubed in my head somewhere. It's what, 35 cubic feet per meter or something. The ones I do have in my head are 7.48 gallons per cubic foot and 3.8 liters per gallon. So you can get there through the units and come up with the mass of phosphorus. So this last one, and you probably want to lay this out in a spreadsheet. So we have total phosphorus load in mass to the stream from this storm. And then we want to know the event mean concentration, which is the flow weighted mean, or it's the mass of phosphorus divided by the total volume, which is used for some things, not used that much anymore. But so what we need to do is we need to figure out the time step by time step, how much flow comes in, how much volume of water, and how much mass of phosphorus. So let's take, maybe we'll do, first of all, I'll do this. Let's do this time step here from 3 to 4 hours. So the volume of water that happens during that time is, I'll type this out, the time step 3 to 4 hours. And again, I recommend doing this in a spreadsheet. So volume of water equals the flow of 40 cubic feet per second times 1 hour. So it's 1 hour time step, right? Between 3 and 4 hours. That's 1 hour there, hour. And then again, like we keep saying, the unit conversion. Then the mass of phosphorus is going to be, the mass of phosphorus is going to be the area under this curve. So the water was the area under the blue curve. Mass of phosphorus is going to be the area under there. So mass of phosphorus is equal to, what is it? Number looks like it's 5 milligrams per liter times, again, the flow is 40 CFS, unit conversion. So the flow times the concentration gives us the mass, and the flow is 40 cubic feet per second times that 1 hour, which is just the number right up here, but I need both those numbers. So the mass of phosphorus is this volume of water that came through in that hour times the concentration of phosphorus equals mass of phosphorus for time step. And then the total volume equals sum of the time step volumes that column. And the total phosphorus equals sum of the phosphorus mass. And so finally, the event mean concentration would equal the total phosphorus divided by the total volume. Do you follow all that? Here's one with just slightly different numbers. So I have my time, and actually some of them, I went ahead and put a 2-hour time step for like this first part because it's got 2 hours of the same thing. And then time, flow, concentration, then time times the flow times the concentration. So hours times cubic feet per second times milligram per liter. That's what I showed here as the mass of phosphorus for the time step. And then I have the flow times the concentration. That's what I showed here for the total volume for that time step. And then a bunch of unit conversions. So I kind of wrote my unit conversions down here. So we get the total mass of phosphorus. That would be the load. And again, this 1200 is before all unit conversions. And then I get the event mean concentration is the total load divided by the total volume of water coming through. And again, the exercise I give you, the numbers are just slightly different from this, but they're pretty close to this. So if you're way off of that, there's a wrong number somewhere. All right, let me know if you have any questions on this.